So here we go with Chapter 1, Matter. First of all, the red spaces are what you fill in your blanks. I think I already said that. The states of matter are generally identified by the placement or arrangement of the particles. And by particles, they could be atoms, and atoms would be for elements. They could be molecules, which is going to be for covalent compounds, or ions, which are going to be ionic compounds, which we'll learn as we go throughout the year. And the movement between them. All particles have motion. Some just have more motion than others. Okay? The kinetic molecular theory, KMT for short, is based on the idea that all particles of matter are always in motion. Okay? There are three basic assumptions of KMT. The first one is that matter is composed of small particles. The measure of the space that the particles occupy, in other words, its volume, is derived from the space between the molecules and not the actual molecules themselves, if that makes sense. So in other words, gas tends to have a much larger volume than solid because there's a lot of space between the particles. A lot of empty space between the particles, but it has a bigger volume. The particles are in constant motion. That motion is different for each state of matter. And then lastly, and remember this is a theory, so in reality it's not really the case, but in theory, when the particles collide with each other, in other words, when they bump into each other or the sides of a container, that they are what we call elastic collisions, which means there's no loss of energy. In reality, that's not the case, but that is the theory or the assumption of the kinetic molecular theory. Everybody have everything they have right there? Okay. So the first state of matter, and I know this is a repeat from like elementary school science, but we still have to make sure we go over it, and that is solids have a very low kinetic energy. They have the lowest amount of kinetic energy of all the states of matter. The particles are vibrating in place. So they can't move around. They're in a fixed position, but they're vibrating, which is why when you're sitting at the stoplight and the car comes by with a real heavy bass, you can feel it in your car, right? It's boom, boom, boom. And because the particles are vibrating, they're able to vibrate in place. Right now you are sitting on vibrating particles. It's just so minute that you can't feel it. But like that's why if you were to bang on the desk, could you feel it in the seat? And that's why, because you cause them to vibrate a little bit more. Okay? Of course, they have a definite shape and volume. They have a very orderly arrangement. So particles of a solid are very ordered in there, and you can see that in the picture. They're real, they've got their spot and they stay there. Liquid is the second state of matter. It also has a low kinetic energy, has more than solids, but it's still a low kinetic energy. The particles are able to slide or glide past each other, okay? But they are still very close together. We can kind of think of them as being able to flow past each other, which is actually how liquid works, is the particles are able to just slide over each other, and then you can pour a liquid, okay? They have an indefinite shape. They do what with their container? They take the shape of their container, right? Whether your water bottle is short and squatty or big and round, they take the shape of that container. However, they do have a definite or finite volume. And as you can see, particles are still really close together, but they're able to they're kind of like jumbled up and just kind of a blob, big blob. The third state of matter is gases. Gases have a high kinetic energy. The particles can separate and move freely throughout their container, and they have an indefinite shape and volume. So gases would fill the room. So if I was to release a gas in here, it would fill, eventually these particles would spread out and fill the room. Some would sneak under the doors and escape that way. That's why when someone makes popcorn down the hall, you can smell it, right? Because the gas part, the odor from the popcorn carries throughout the area, and then everybody wants popcorn. Unless it's burnt popcorn, that's worst. Yes?
On the liquids one, there was another blank that wasn't on the slideshow. It said, relatively blank.
Oh, incompressible. I'm glad you asked that. I didn't realize that was in there. I need to add that bullet point in. They're relatively incompressible. Whereas gases are highly compressible because there's a lot of space between the particles, and you can push them together. So what about solids? Compressible or incompressible? Yeah, incompressible. Yes, ma'am.
So when you look at a pressure situation, if you were to compress, does that mean that for liquids, the pressure is going to increase faster?
Well, for liquids, you really, when we're talking about pressure, we're usually talking about gases, okay? So for liquids, you don't really have a pressure for liquids because their particles are already close together. But like if you're thinking of like when you go underwater and you go down, it's the pressure that the water is putting on you and in your body. That's why your ears pop when you go too deep or whatever. So when we measure, there is pressure, but it's not the same as for gases. So when we say, like we can have compressed air, you have a tank with air in it, or liquid, or not liquid, but like nitrogen and oxygen. And what they've done is they've taken the gas and pushed it together, okay? And if you push them close enough together with enough pressure and a low enough temperature, that's how you can liquefy it. That's how you get liquid nitrogen and that sort of thing. But when we're talking about pressure, we tend to be talking about gases, okay? But when you're going like diving or whatever, it's the pressure that the water is putting on you as you go down. Yeah. Okay? The fourth state of matter is called plasma. And it has got a very high kinetic energy, very, very high kinetic energy. The particles are colliding with enough energy that they're breaking into charged particles. So they're kicking out electrons is what's happening, okay? You can write that down, kicking out electrons. Let's write that down. Okay? They are gas-like in their behavior, and they also have a variable shape and volume. They are electrically conductive, which means they'll conduct electric current. And some examples of plasma in your everyday life are stars, cathode ray tubes, fluorescent lights like we have in here. Those would all be examples of plasma. Not so much any more plasma TVs around. Does anybody still have an old plasma TV or a grandparent that has an old plasma TV? Those didn't actually last long. They went straight, they kind of skipped. Not that many people ever had them because they had them out for a while. They were very expensive, and then they came out with them. There's Gremlins that does that sometimes. I hope it doesn't do it a lot. I think my bulbs don't keep doing it. Not, we're going to be blinking. Yeah, it's going to do it for a while. Thank you. There's some examples of plasma. Oh, come on. It won't show up on the video, the flashing. It's only showing up on there. So after we get done with the notes, I'll turn it off and on. That usually helps. So there's some examples of the fourth state of matter of plasma. Lightning is an example of plasma. And then draw and describe the behavior of the three main states of matter. So you're going to need to draw this if it will stay and stop doing that. We're going to try this. I am going to pause the video while y'all draw that and see if I can get that to stop doing that. Okay, now that we were done drawing, we're going to move on. I will just freeze it at each slide since it seems to be blinking. We're going to do a workaround. So let's talk about two types of properties of matter, as physical and chemical. I'll let you write that down. And we'll talk about those more extensively, which is the topic of today's lesson. We're going to do the physical and chemical properties and changes. Then tomorrow we'll do classification of matter. So physical, oops, freezed on the wrong one. There we go. Physical properties are properties that can be observed without changing the identity of the substance. So it's usually things that we can taste, touch, see, hear, or smell kind of thing. So if I see that the solid is shiny, then that's a physical property. If I smell that roses are red, violets are blue, roses are red would be a physical property. I can look at a rose and see that it's red, and it doesn't change it, so it's a physical property. Okay. There are some physical properties that we can measure. For instance, the boiling point of water is 100 degrees Celsius. I can measure that. If I boil water and measure that, is it still water? Yes, it didn't change it, so that would be a physical property. Within physical properties, there are two types of physical properties, and that is extensive and intensive properties. Okay? They're still physical properties, we're just a little bit further subdivided. An extensive property depends on the amount of material present. Does not depend on what it is. So I could have 5 grams of salt 5 grams of gold, 5 grams of feathers, that would still be an extensive property because the property would be 5 grams. Doesn't matter if it was salt, gold, or feathers. It was 5 grams. Okay? An intensive property, however, does depend on the identity. The way I remember which is intensive, identity, both start with I. That helps me remember them. Okay? But that's things like the boiling point of water is 100 degrees Celsius. That is because it's water. If I was to boil something else, say acetone, it would have a different boiling point. Not everything in the world boils at 100 degrees Celsius. Okay? Another example of an intensive property would be something's density, which density is basically thought of as the concentration of matter. So let's go back to that 5 grams. If I had 5 grams of salt, 5 grams of gold, and 5 grams of feathers, the density of all 3 of those materials would be different, right? Which would be the highest? Gold would have a much higher density than the feathers, okay? But 5 grams is still 5 grams. So the 5 grams would be an extensive property, but the density of each one of those would be an intensive property, okay? Roses are red, violets are blue. The roses are red because that's an intensive property, okay? Roses can also be other colors, but we're talking about that point, okay? Any questions on the difference between intensive and extensive? Those are ones that kids tend to get mixed up on tests. I don't know why. I think because they just don't think to study those two. They just know physical properties, and then they don't go further and do the extensive versus intensive. Properties and changes of matter. So a chemical property is something that has the ability to turn a substance into a new substance. It's not actually doing it, it just has the ability. In other words, wood has the ability to burn. Okay, and so if I burn wood, it changes into a new substance. But the ability to burn is its chemical property. Okay, iron has the ability to rust. If it actually rusts, it goes on to be a chemical change. But the property is it has the ability to rust. Okay. So things like combustion has the ability to combust, like gasoline, it has a combustion. Before it actually combusts, it's a chemical property. It has that ability. Okay? Is everybody done writing on that slide? Okay, I'll wait. Okay. Properties and changes. A physical change is the effect of the physical properties can be easily reversed. So, in other words, if I, and not every physical change can be reversed. So, like if I tear a piece of paper, it's still paper, but I can't really put the piece back together. But that's still a physical change because when I tear a piece of paper, now I have 2 smaller pieces of paper, but is it still paper? Yes. Okay. If I take water and I boil it, it becomes steam, right? So then, but is it still water? Yes. If I take that water and I freeze it and it becomes ice, is it still water? Okay. What is the formula of water?
H2O.
H2O. What is the formula of steam? What is the formula of ice? No, it's H2O cubed. There it is. No, I was making one of my corny jokes, which I have plenty of. And I told first period, I really like corny jokes. If you have corny jokes, bring them to me. Love them. If you don't like corny jokes, I'm not going to apologize. You're just going to have to suffer through it. Okay? I'm here all day. I have to entertain myself. Okay? Hold on one second. Let me finish a couple of things. Dissolving is one that a lot of kids miss. It is a physical change. Okay? If I dissolve salt into water, can I get that salt back? How? Evaporate the water. The water goes away. The salt stays behind. So that's a physical change. So dissolving something is a physical change. Okay? Melting something. If I melt chocolate, is it still chocolate? Yes, and if I stop melting it, it solidifies back, right? Unless it's being digested in my stomach. Okay. Did you have a question, Sophia?
Oh, I figured it out.
Okay. All right, so let's go to chemical change. Whoops, I went too far. I got a little happy with this. Oh, phase. No, I didn't. Phase changes, of course, are physical changes. We just talked about that with the water and the ice and the steam. Okay. The names of the phase changes you probably are familiar with is in terms of, freezing and melting, opposite processes, but solid and liquid changes. Evaporation and condensation. Two that you might not be as familiar with is when a solid goes directly to a gas, it's called sublimation. Or if it goes straight from a gas to a solid, it's called deposition. The way I remember it is if a gas is going to a solid, it deposits something, so that's deposition. Okay? An example of sublimation is anybody ever played with dry ice or seen dry ice. It's solid, and you put it out on the counter, and it goes straight to a gas. Okay? Anybody's grandparents still use mothballs? Have you heard? They're like a little crystal thing. They have this distinct smell. You put them in there, and they just evaporate. Okay? That's how solid air fresheners work. Okay? They go straight from the solid of the air freshener. Now, that's not the way the Glade and Febreze that are liquids work. That's not sublimation. But it goes from a solid straight to a gas. Okay? So that sublimation and deposition are probably new terms for you guys. So, chemical changes produces a new substance. Okay? And there's ways to tell if a chemical change happens. And there's signs of it, basically. This is a new thing I found at the end of last year when I was doing my notes, and I loved it, and I'm using it. So basically, if the substance farts, it's a chemical change. The F stands for fizzes, meaning a gas is produced. Because if a gas is produced in a chemical change, it's going to bubble out. Okay? If there's a smell produced. Okay? Now, that's not to say it didn't start out with a smell. For instance, roses smell a certain way because of that would be a physical property. But if I mix two substances together and it produces a very distinct odor, then that would be an example of a chemical change. Sometimes those odors are bad. Sometimes they might actually smell good. Okay? If a replacement happens, did I replace and get a new substance? If the temperature changes, both hot and cold. Okay? What's it called if I produce heat? What kind of reaction is that? Do you remember from junior high? No, exothermic.
Oh,
Because you're releasing energy from the system or releasing heat. And then endothermic is when it gets cooler. Okay? And that's because it's absorbing energy. And then if a new substance is produced. Okay? If I burn wood, is it the same as when I started? No, I have this new substance of ashes. So that's an example. Okay? So when we're talking about physical and chemical changes, they all involve some transfer of energy, either absorbing it or putting it out, okay? Which brings us to the law of conservation of energy, and that states that energy cannot be created nor destroyed. It is only transferred in a chemical or physical change. So it's transferred somehow. Examples of that is your body uses the energy from chemical changes involved when you digest your food. How many of you ate breakfast this morning? So your body's busy breaking that down so it can utilize that energy. Okay? And then, of course, the weather cycle or the water cycle uses energy to produce the physical changes of evaporation and condensation. Okay? When it's really, really cold outside, it's using energy or transferring energy to freeze or melt ice and snow. So let's practice, except that it's not going to let me write if I freeze it. So let's see if it's stopped doing it. If not, I'll get up there and label it. Okay, so we're going to label these as either chemical or physical properties, not changes. We're talking about properties here. If they are chemical properties, then we're done labeling them. If they're physical properties, we're going to also state whether it's an intensive or an extensive. Okay? So let's see what happens. Y'all may just have to deal with the blinking. Yeah. Combustibility. Is that going to be chemical? So we're going to put a C there. I can get my pen to work. C. How about color? Physical, and is that going to be intensive or extensive? Intensive has to depend. Roses are red, the violets are blue. That's intensive. How about reacts with water? Definitely chemical. How about smell? Physical, intensive, because we're talking about properties here, not changes. Okay. Length. Extensive. Yeah, I can have a foot of wire, a foot of string, a foot of hair. Melting point. Physical, intensive, right. Melting point of ice is 0 degrees Celsius. Melting point of chocolate is in your hands. I don't know what that temperature is, but chocolate melts in your hands. Okay. How about density? Intensive, depends on what it is. Solubility, which means does it dissolve? Physical. And would that be intensive or extensive? Intensive. How about malleability? What is malleability? Y'all remember? Yeah, someone taught y'all well. Ability to hammer it into a thin sheet. So that would be a physical, intensive. Yeah. How about reactivity? Chemical. Volume. Extensive. And then lastly, ductility, which means can I pull it into a thin wire? Intensive. So there was, honestly, there's quite a bit more intensive properties than there is extensive because there's only so many ways we can measure the amount of something. Okay? So let's go on to the next slide and practice that. And then you are done and free to work on your little packet of practice. Hey, I think we might have, I don't know what we did, but it seems to have stopped. Now I'm afraid to turn it off because I don't want it to start again. All right, so these are types of changes. So we're actually going to make these changes. So tearing a cloth, physical. So we don't need intensive, extensive here because we're changing it. Physical. How about pounding into a sheet? We actually go ahead and make it malleable. It is. Dissolving salt in water. Physical because I can get it back. How about fermenting wine? Chemical. Electrolysis. If you don't know what electrolysis is, it's passing an electric current through something. And it would be a chemical. It causes a chemical change. So if I pass an electric current through, say, water, I can separate it back into oxygen and hydrogen gas. Yeah. Yeah, it is cool. Okay, maybe we will. Maybe we will. Melting. Physical. I got this down. Breaking a window. It's also called destruction of property. Stirring. Physical. Boiling water. Physical. Exploding something. Digesting your food. Definitely chemical. It does not come out the way it went in. Distillation, which is boiling. Distillation is a process in which you separate things by their boiling points. So if I'm boiling it... Oh, that one's not on your paper? Okay. Is washing clothes?
Yeah.
Okay. Well, what is washing clothes? Physical. Distillation is physical because you're boiling it. Anytime you're boiling something, it's not changing it. It's just putting it into the vapor phase. Okay? And I believe that is where we stopped today. Yep, that's where we stopped.